So, welcome everyone to the second session of the third day. So, in this session, we will have two talks. Please remain muted during the talk, and you may unmute yourself to ask questions during the talk. You may also ask questions over chat. So, without further ado, we are very happy to have Professor Sanjaye Ramgoolam from Queen Mary, University of London, who will talk about quantum mechanics of bipartite ribbon graphs and Kronecker coefficients.
Thank you very much to the organizers for organizing this very stimulating conference at a very interesting intersection of topics, and for the opportunity to speak here. This is based on work done with Joseph Benjeloun, who is a collaborator. I have worked on tensor models for a few years. And this is primarily based on this paper, which appeared a few months ago. So yeah, as was said before, I'm happy to take questions during the talk and at the end as well. So many quantities in symmetric group representation theory. So if you think about n objects and permutations of n objects, a symmetric group is Sn. Many quantities in the representation theory of Sn are constructible combinatorially. So I'll explain what that means. So, for example, dimensions of irreducible representations or Littlewood Richardson coefficients, they are constructible combinatorially. So, for example, representations of S3 symmetric group for 3 elements correspond, the irreducible representations, the irreps correspond to Young diagrams. So this is one Young diagram for S3. And if you ask what is the dimension of that irrep, that's a 2-dimensional representation. And you can get that number 2 simply by counting what are called standard Young tableau. So these are labeled versions of this Young diagram where you enter the numbers 1, 2, 3 with a condition that the numbers have to be strictly increasing along the rows and along the columns, down the columns. So for that reason, the first entry here is just 1, and this can be 2, 3 or 3, 2, and these 2 possibilities, you count them, so you find there are 2 possibilities, and you learn that the dimension of that irrep is 2. Another quantity, the Littlewood Richardson coefficient, has an interpretation in symmetric group representation theory. So if you take this Young diagram here with 6 boxes, there's a corresponding irreducible representation of S6, and the dimension is 16. And S6, if you're permuting 6 things like 1, 2, 3 up to 6, has a subgroup S3 cross S3 consisting of permutations of just 1, 2, 3 among themselves and 4, 5, 6 among themselves. So S3 cross S3 is a subgroup of that. If you're given an irrep of S6, this one here, you can ask how many times do the different irreps of this subgroup appear when I take this irreducible representation of the big group and I decompose it as representations of this subgroup. So representations of these subgroups are Young diagrams with 3 boxes. So for example, how many times does this representation of S3 cross S3 appear when I decompose that in terms of S3 cross S3? Well, the answer to that is 2. And that number can be obtained without actually doing any representation theory, simply by taking this Young diagram here, leaving its boxes unlabeled, taking this Young diagram and labeling the first row of boxes 1s, the second one 2, and then putting these guys together to build bigger Young diagrams according to some rules. So this is called the Littlewood Richardson rule. And you don't really need to I won't describe what it is, but these are the two diagrams that you can draw according to this rule. And the fact that you have exactly two tells you that this multiplicity of decomposition of this representation into this representation of the subgroup is exactly 2. So that's a combinatorial construction of something defined in terms of representation. So these are representation over complex numbers. You have matrices representing all the group elements, in general complex, and we're talking about how to reduce them. But the answer to this reduction is entirely in terms of discrete, a finite discrete set of objects and some labeling rules. So these reduction, although the representations are defined over C, using this reduction rule, you are just working with integers, discrete objects, and counting. And you can get these multiplicities of reduction from this group to that subgroup in general, Sm plus n down to Sm cross Sn. We in physics usually first encounter Littlewood Richardson in the context of tensor products of UN. Representations are tensor S. How many times does this third representation appear there? These two are related by something called Shuval Duality, which is a theorem that generally relates continuous group representation properties to discrete groups. So that kind of plays a role in things. There's another quantity, the characters of Sn, which are specified by a Young diagram R and a conjugacy class of the symmetric group. Again, there is a combinatoric rule. You take the Young diagram, there's some labeling rules that depend on the conjugacy class you're choosing. And once you have labeled them, you call the label thing a tableau. And for that tableau, there's a height function, a -1 to the height function. You calculate pluses and minuses, and you get an integer. So again, there's a combinatoric construction for the character. And this algorithm is called the Monahan-Nakayama lemma. So there's another very interesting quantity associated with Young diagrams. If you take Sn, take the 3 irreps of Sn, so 3 Young diagrams with exactly n boxes. Correspondingly, we have 3 irreducible representations. Take the tensor product of them. Let your Sn elements act as they would usually in a tensor product. So sigma is a group element. It acts like this. Now, this action of the diagonal Sn, you see, how does this decompose under the different representations of this diagonal action? And you can ask how many times when you decompose that, the trivial representation appears. That number is called the Kronecker coefficient. Equivalently, it is the number of times, if you take R1 tensor R2, how many times does R3 appear in that tensor product decomposition? So that's a group theoretic quantity, in a way quite like the Littlewood Richardson, which was slightly different, but same sort of thing. So you might ask, is there a combinatorial construction for the Kronecker coefficient? And that's a question that has been asked for a long time. There is no known answer in general for general triples of Young diagrams in terms of any concrete combinatoric construction where you can build something and count it and get that number, like we have for these other things I described. There are formulae, for example, in terms of characters, where you're summing over all group elements or all conjugacy classes. And that's in general is sum of a very large number of things. Each one of them is an integer. So it's not one thing you can say, okay, that thing is, if I could count that one thing, I would be counting Kronecker coefficients. So this kind of formula doesn't do that. And we don't have an analog of the Littlewood-Richardson rule. So, the question is there some discrete set of things you can count, which will be the Kronecker coefficient? So, building on work on tensor models over the years, somehow there are some insights that can be brought to bear on this problem. And that's what I will describe. So we will approach this problem by using a family of algebras, K of n, one for every positive integer n. These algebras have a lot of information about tensor model observables, counting of observables, large n phase transitions, correlators, and so on, which are of interest in the context of holography. For example, the rapid growth of the dimension of this algebra as a function of n implies a vanishing large n Hagedorn temperature. So here,
rapid growth means exponential or
it's
factorial?
super exponential. It's like n factorial.
Factorial. I see. Thank you.
N factorial, yeah. And that has a consequence that, exponential growth leads to Hagedorn temperature, super exponential leads to vanishing sort of Hagedorn temperature. And that has been remarked in the literature on tensor models. So here we will focus on a mathematical application of this algebra. So what is K of n? So K of n is a subalgebra of C of Sn tensor C of Sn, where C of Sn is the group algebra of the symmetric group Sn. So it's a vector space of dimension n factorial. Elements in C of Sn look like linear combinations of permutations, and you multiply them. If you two of these linear combinations with some complex coefficients, you can multiply them using the group product. So this is going to be a subalgebra, which I will specify. So this algebra comes up in thinking about tensor invariant. So in particular, the following problem. Let phi ijk be a tensor variable, 3 index. Each index is in the fundamental of un cross un cross un. And this is the conjugate, again, un cross un cross un. So fundamental of v tensor v and v bar tensor v bar tensor v bar. So in tensor models, we are interested in polynomial invariant functions that you can build out of phi and phi bar, which are invariant under un cross un cross un. So I have one un that acts on the I of this and the I of that, and another un that acts on the second index, and another un that acts on the third index. And I want to build polynomial functions of phi and phi bar, which are invariant under un cross un cross un. So how do you build un invariants? Well, essentially, you contract indices. So more formally, if you take Vn tensor V bar and you take a tensor product decomposition of that, there is the adjoint and there's the invariant. What does the invariant look like? Well, EI tensor E bar J here, invariant is made from contracting I here, or you have Ji and is it delta Ij. Now, if you have, let's say, little n copies of V, so a bunch of copies of V, and little n copies of V bar, how do you make the most general UN invariant? And the answer is the following. You take your states Ej1 up to Ejn, E bar I1 up to In, and you contract the J's with the I's, except that you can permute which of the J's contract which of the I's. You could have just first have I1 J1 up to In Jn, but if you permuted the indices here using a permutation sigma, you would get another invariant, and the n factorial choices. So each of these invariant is one, each of these things here, each of these linear combinations here is one invariant. And we know that this kind of exhausts all the invariants for little n less or equal to capital N using Shuval duality. Shuval duality says that you take the fundamental, take the n-fold tensor product, you can decompose that. This has an action of the un that we were talking about, this capital N, but also that the different factors can be permuted. So there's an action of un and Sn, they commute, and you can sort of diagonalize their action simultaneously. And there's a decomposition in terms of a direct sum of Young diagrams. Representations associated with Young diagram R for un and Sn. So using that decomposition, if you take V's and V bars, you have two things like that, R's and S's. To build a UN invariant, R must be equal to S. This is V bar. And then but there's a multiplicity here. So you get the formula n factorial from Shuval duality. And this Shuval duality also tells you what happens when you have finite n. you just some of the dimensions of Sn reps with some constraint, which is less than n factorial. So basically, this counting is reliable, and you can also do it at finite n when the rank of the tensors is finite. So there's a nice diagrammatic understanding of these permutation contractions. So E's and E bars you contract, so that these are E's, these are E bars. Contraction is just joining the lines. If you have two E's and two E bars, you can just join the lines straight, or you can join them with a permutation. In general, you have n lines above and n lines below for the E's and the E bars respectively, and there's a permutation that joins them, and for each of them you have an invariant state. Now, in this tensor model problem, we have three indices, the i's, the j's, and the k's. So we're going to have Vn, tensor Vn, and the V bars. This is for the phi's, this is for the phi bars. I am interested in degree n, little n. So I'm going to have n copies and n copies of phi bar. And it's symmetrized because, you know, the phi's are bosonic variables. So that's why there's a sim n there. Okay, so essentially, how do you build these invariants of tensors? You take these phi's, you can put them here, you can align them, and these are the I indices. The black lines correspond to the I indices, the blue lines, the J indices, the red lines, the K indices. And I want invariants of these three separate UNs, UN cross UN cross UN. So to build, I have to therefore contract the black lines with the black lines, and there's an arbitrary permutation here, the blue with the blue, and the red with the red. So there are three permutations which can be used to build invariants if I have, you know, n-fold tensor product of this, n-fold tensor product of that. However, this is a little bit redundant because this is, if I take n factorial, n factorial, n factorial, that's too many invariants. And the reason for that invariance is precisely the symmetrization of the phi's and the symmetrization of the phi bars. So how does that translate in this permutation language? Well, basically, you build invariants from sigma 1, sigma 2, and sigma 3. And if you take this triple of permutations and you have one permutation on the left, I'm multiplying these all three permutations on the left by gamma 1 and all three permutations on the right by gamma 2. If I do this multiplication for any pair gamma 1, gamma 2, I will get the same invariant. And that's essentially implementing the sim n, symmetrizing these phi's, and or permuting these phi's shouldn't affect the invariant. Permuting these phi bars shouldn't affect the invariant. So that amounts to saying that the invariants correspond to triples of permutations with this equivalence. Now, this is a known mathematical equivalence called a double coset. We have a product of three symmetric groups, and you're modding out by the diagonal action on the left and the right, precisely this equation. And there are these things which correspond to these kind of graphs where you have black and red and blue lines. So that's a combinatoric thing you can draw. So how do we count? How do we get a formula for the counting of the dimension of K of n? The fact that there is this description in terms of gamma 1, gamma 2 acting on triples is very useful. Whenever you have a group here, Sn cross Sn acting on something, you can count the orbits and you can count the size of this double coset. So the orbits, basically there's a formula called the Burnside lemma, 1 over the size of the group, n factorial square, and the number of fixed points of that action is the weight. So the number of fixed points can be, so more explicitly, what does that say? It says that gamma 1, sigma 1, gamma 2 is the same as sigma 1. This is a delta function on the group, which enforces the fact that this is equal to, this whole thing is equal to 1, this whole thing is equal to 1, so this product is equal to sigma 1. So that's exactly what fixed points of this action means, that these three delta functions are satisfied. So manipulating these delta functions a little bit, you find a nice formula for the counting of invariants, of independent invariants, which is that you sum over all partitions of little n. Little n is the degree of my invariance, and the symmetry factors of these partitions. So partition is a splitting of n into a bunch of integers, integers I with multiplicity pi. And in terms of these i's and pi's, there's a symmetry factor for the partition. So there's a nice concrete formula for how many invariants there are. Now, these delta functions on symmetric groups, they're just a function on the group, which is 1 if sigma is the identity and 0 otherwise. They have an expansion in terms of characters, irreducible characters of Sn. And if you use this character formula for these deltas, you arrive at another expression for the number of invariants. And that number is the sum of the squares of Kronecker coefficients, the thing we were interested in. So the number of invariants that you can build from little n copies of phi's and phi bars is the sum over triples of Young diagrams, R1, R2, R3. And for each triple of Young diagrams, each of them with n boxes, you take the square of the Kronecker coefficient, and that's a formula for the number of invariants in terms of Kronecker coefficients. So the same thing has two different descriptions, sum of Kronecker coefficient squares and these number of graphs which correspond to these permutation triples. Now, just to make it a little bit more familiar to in sort of large n matrix theory, these triples of permutations actually have an even nicer description, which is more familiar from large n gauge theory. So there's another combinatoric description which comes from kind of a gauge fixing. So gamma 1 and gamma 2 can be viewed as gauge symmetries acting on triples of permutations. And there is a gauge fixing which can be done, which essentially you have these triples, you set gamma 2 for a given triple, you can take gamma 2 to be sigma 3 inverse, which sets this one to 1. And you have these permutations. So if gamma 2 is, I choose gamma 2 to be sigma 3 inverse. So multiply on the right, I get 1 here, sigma 1, sigma 3 inverse, sigma 2, sigma 3 inverse. So I get tau 1, tau 2, which I've just renamed these two guys. On the other hand, I can take this triple, multiply with gamma 1 on the left, and then multiply by the inverse of that. Then I get 1, and I get this conjugated version of the taus, where I have this is equivalent to that. So let's not worry too much about the details. The point is that we took this permutation equivalence relation expressed in terms of 3 permutations with some equivalence. Here we rephrase it in terms of 2 permutations with some equivalence. And this is a known known kind of equivalence class of permutations, which is related to bipartite ribbon graphs, which are essentially graphs embedded on surfaces, or in other words, large n diagrams. So these pairs of permutations subject to this kind of permutation equivalence, they describe precisely bipartite graphs. So graphs with 2 kinds of nodes, black and white, and the edges always go from black to white. And these graphs are embedded on a surface. So locally, every vertex has an orientation. So just to concretely show you this pairs of permutations. So if you have S3 pairs of permutation, identity, identity, the corresponding bipartite graph is the one where I have, I'm in S3, so I'm going to have edges labeled 1 to 3. This is the identity permutation. So as I go around this guy, I get 1 goes to 1, 2 goes to 2, 3 goes to 3. So from the permutation, I read off the structure of the graph, and likewise for the white vertices. And different pairs give you different graphs. So here, 1 identity again, 1 goes to 1. Here, 1 goes to 2, goes to 3. So that's different ones. And some of them, if you have 3 edges, some of them can, all of these are genus 0. This is genus 0, this is genus 1. And if you kind of just thicken the lines of these graphs, you get more familiar looking. Take this guy, thicken the lines. Take this guy, thicken the lines. You get familiar looking double line diagrams, which come up if you're kind of doing Wick contractions in ordinary matrix theory. So essentially, this tensor observable counting gives you the enumeration of all matrix double line graphs with a fixed number of edges. So there's a nice combinatoric relation to large N diagrams. So great. So what is K of N? I said I want to talk about this algebra K of N. So this algebra K of N is directly related to these ribbon graphs. Essentially, this is a subspace of the group algebra of C of Sn tensor C of Sn. So things here look like linear combinations of pairs of permutations. And then I have this equivalence of conjugation of both permutations. So if I look for linear combinations which are invariant under that diagonal conjugation, I will get a subspace. And it turns out that subspace is a subalgebra. So associated with that equivalence of permutations, there is an algebra which is K of N. Essentially, you take, you have these permutations tau 1, tau 2. There was some equivalence. So tau 1, tau 2 could be related to some other tau 1, tau 2 by this diagonal conjugation. So therefore, all these tau 1, tau 2s form orbits under a group action. So given an orbit, which is a fixed index for the orbit here, I have some pair of permutations, and I have different permutations within that same orbit. So I can take an orbit average. You can also write it in terms of this diagonal conjugation. This is gamma, gamma inverse, gamma, gamma inverse. So, so basically, there's a concrete way to write from the graph these elements inside C of Sn tensor C of Sn, which are invariant under diagonal conjugation. So that's a typo here. That's a gamma. Great. So basically, this algebra K of N has a basis labeled by distinct bipartite ribbon graphs. So great. So we have this algebra K of N. It has its size. The dimension of that is the number of ribbon graphs. And it's also the sum of squares of Kronecker coefficients. So what this is telling us is that the sum of squares of Kronecker coefficients has a nice combinatoric interpretation. The sum of squares is simply the number of ribbon graphs with n edges. So then the next question is, can you refine this link between ribbon graphs and Kronecker coefficients to give you an interpretation in terms of ribbon graphs for a fixed Kronecker coefficient, for a fixed triple of Young diagrams? So that's the question we address in the latest paper. And so we have this K of N, which is a subalgebra. And the way we approach this question is to go to this algebra K of N and think about these two ways of thinking about it. On the one hand, there is a basis set labeled by ribbon graphs, and there is also a basis set labeled by something related to this side. So what is that? So that turns out there's a Fourier basis of concrete things you can write down using Clebsch-Gordon coefficients. I'll write it more explicitly later. But there is a basis of things which are which are labeled by triples of Young diagrams, and for each triple, there's exactly C squared. Tau is an index that goes from 1 to the Kronecker. This goes from 1 to the Kronecker. So the number of these things for each triple is exactly C squared. So basically, within this algebra, now there is a subspace labeled by triples of Young diagrams, which is the span of these Qs. And now the question of identifying C squared is to how do you pick out these Qs? So what I will show is that these subspaces labeled by triples of Young diagrams, whose dimension is C squared, can be picked out by choosing some appropriate operators and looking at the eigenvalue equations for these operators. And these eigenvalue equations, they are very nice because they just involve integer quantities. And as a result of that, by solving these integer matrix equations, you find that there are nice linear combinations of the ribbon graphs, which form a sublattice inside the full lattice of integer linear combinations. So the upshot is going to be that there is inside the lattice of ribbon graphs, which is the set of integer linear combinations of Riemann graphs, there is a sublattice whose dimension is c square, the square of the Kronecker coefficient, and there's a concrete algorithm based on an integer matrix that can be used to construct that sublattice. So that's essentially the plan of the talk. Maybe I can take some questions if there are any at this point. If there was anything unclear, I said. Okay, so in that case, I will continue. Here's the plan of the talk. So to set up this kind of sublattice story, we need to have this kind of map between two different ways of thinking about the same space. And that map is basically Fourier transformation. And there's a version of Fourier transformation on the group algebra or the center of the group algebra. And then this will be useful. It'll give me some information that I will use later. And also this kind of thing can be generalized to a Fourier transformation on K of n itself, this algebra. And it'll give us a Fourier transformation between a Riemann graph basis and a basis labeled by Young diagram triples. And then I will show how this Fourier transformation can be used to obtain sublattices with dimension equal to c squared. And these these algorithms for building these sublattices can be interpreted in terms of quantum mechanics on this algebra. In other words, this K of n can also become a Hilbert space, and we are doing quantum mechanics on that. And in that setup, it's natural to think about eigenvalue problems. And in fact, turns out that these problems we're thinking about are eigenvalue problems for Hamiltonians in this quantum mechanics. And finally, I'll talk about the link to Belly maps. Great. So there are nice Fourier transforms on the group algebra of Sn and also on the center of the group algebra. So the center is simply the subspace of the group algebra which commutes with everything in the group. So if you have any conjugacy class mu, you take the sum of all the permutations in that conjugacy class, you get an element in the group algebra, which is in the center. It commutes with everything. Now, these central elements obey a nice closed algebra. If you multiply T mu and T nu, these are two different conjugacy classes, which are in turn partitions of n, if you're looking at Sn. If you multiply two of them, you can re-expand them in terms of the T's, and these are some integers. And there's another basis for the center of Sn, which are labeled by Young diagrams. You just take the sum over permutations and you weight them with the character in some irreducible representation. So you take that guy, and these things obey nice projector-like relations. And what's the connection between the T's, the conjugacy class labeled central elements, and these projector central elements? If you multiply them, T mu times this projector, you just get the normalized character. So you take the character divided by the dimension times the projector itself. So these normalized characters have a very nice property. So this guy, I told you, there's a Monahan-Nakayama lemma, which is an algorithm that tells you this is an integer. But turns out that this ratio is also an integer. And this follows because you can get these PRs by kind of solving the, you can think of this as an operator on the center, and the action of that operator on the center is given by these matrices. The matrices are integer. So that integrality has important consequences. It says that these ratios themselves are integers. So this integrality will be useful later. Another useful fact that will be useful when I get to the next step is that if you look at the center of Sn, how many distinct things can we think of here? So we said there is one for every conjugacy class, and that means there's one for every partition of n. Okay, so partitions of n, they can grow like e to the root n. So every partition of n, that's much bigger than n. The number of partitions of n is much bigger than n. But you can take those conjugacy class containing a single non-trivial cycle of length 2, single non-trivial cycle of length 3, single non-trivial cycles of length n. And if you take this list of n-1 central elements, they generate the center in the sense that you multiply them and take arbitrary products and linear combinations of these products, that spans the whole of the center. So there's a set of central elements here. Related to this fact is that the normalized characters for these guys, these normalized characters, they distinguish Young diagrams. So if I list these normalized characters for one Young diagram, and then I scan through all possible Young diagrams and have this list for the different Young diagrams, this list of normalized characters distinguishes. No two distinct Young diagrams have the same list. So this generates the center, and these normalized characters are kind of distinguished Young diagrams. So basically the point of this will be that these T's can be used to detect Young diagrams, this set of T's like this. And in fact, I said T2 up to Tn can distinguish all Young diagrams. These little experiments you can do. Even in fact, if you work with S2, S3, S4, up to S, all these guys, just a single normalized character can distinguish all the Young diagrams. If you take two normalized characters, you can distinguish all Young diagrams for Sn up to 14. And if you take 6 of them, up to 79. So basically for us, it suffices to know that if you just take n of them, you can generate everything and you can distinguish Young diagrams. By the way, the problem of finding what's the minimal number of these T's you need to distinguish Young diagrams was motivated by studying integrability and information loss, this paper of Balasubramanian and collaborators, which was related to distinguishing LLM geometries using a limited number of multiple moments of the bulk ADS fields. And the connection to symmetric groups comes in because you can build these half BPS operators using Young diagrams and associated projectors from the symmetric group. So this kind of, if you dig into it, there's some relation to holography. So great. So just like there's a Fourier transform for the center of the group algebra, there's also a Fourier transform for the whole group algebra. Now you don't sum over sigma with characters, but over the matrix elements in some orthogonal representation. You can sum over sigmas with these matrix elements, and if you count how many of them are there, you can exactly n factorial. So this is one basis. These Q's form another basis. So this notion of Fourier transform between two kinds of things continues to work for the whole group algebra. And if you take this Q, these basis elements of C of Sn labeled by Young diagrams, you apply the TKs, you get these normalized characters. So to identify a given Young diagram, you just need to act with the TKs and find the eigenspaces. So this will be useful when I go to K of n, Fourier transform on K of n. So, so to summarize, we had a subalgebra K of n inside C of Sn tensor C of Sn, which is invariant under diagonal conjugation by gamma. And one basis in this algebra was given by these sums over permutations. Basically, you take some equivalence class under this conjugation, and you pick a pair of elements there, and then you average, and then you can also write it as a sum over all the different elements in that orbit for that particular pair of permutations. So these are things directly related to a particular ribbon graph. So R ranges over the particular ribbon graphs. And for each such thing, there is an element in the algebra K of n. Now, there is another kind of element which is more labeled by Young diagrams. And essentially, we are looking for elements inside Sn cross Sn, but I have to make sure that they're invariant under this diagonal conjugation. And there is a bit of, so these are just matrix elements of permutations in some E-reps, and these are Clebsch-Gordon coefficients. It's a somewhat complicated looking formula, but actually, conceptually, it's quite simple. You know, you have these matrix elements, these elements in the group algebra of C of Sn labeled by a Young diagram and a pair of indices labeling states. Diagrammatically, you could draw this like that. If you have 3 representations coming together at a point, there's an associated Clebsch-Gordon coefficient. There's a multiplicity there. And so essentially that formula is just a diagram where you have two of these Qs, and then you have two vertices which correspond to two Clebsch-Gordons. Each of these vertices has a multiplicity, and the range for these multiplicities is from 1 to the Kronecker coefficient, and the total of these guys is therefore C squared, because tau1 and tau2 range over the Kronecker coefficient for that triple of Young diagrams. So this is the Fourier basis, and these are Clebsch-Gordon coefficients, and so on. So these Fourier basis elements, they have the property that they are invariant under diagonal conjugation. So they indeed live in K of n. They have a nice multiplication property that if you have one set of R's and another set of R's, you get 0 unless this triple is the same as that. And the structure of the multiplication is kind of similar to elementary matrix multiplication. You get a tau2 prime, tau1, tau3. So what these Qs essentially are doing, you have a nice associative semi-simple algebra, K of n, and such algebras have a matrix decomposition called Wedderburn-Artin through the Wedderburn-Artin theorem. What this formula is giving you is a concrete decomposition in terms of as matrix blocks. So great. So you have these concrete subspaces, Fourier subspaces labeled by triple of Young diagrams. Their dimension is C squared. Tau1 goes from 1 to C squared and so on. But actually building these Qs explicitly using this formula is complicated. You have to find Clebsch-Gordons of Sn for general n. It's complicated. So we don't really want to do that. What we want to do is say that these Young diagrams can be detected by these TKs I talked about before. And I want to think about these TKs in the geometrical basis, because it's another basis for the same space. So take the TKs, sum of a permutation in a given conjugacy class, act on the first slot, you had C of Sn and C of Sn, or you act on the second slot, or you act simultaneously on both slots. You get three kinds of TKs, central elements in the group algebra. So these TKs, when you act on the Qs, so you have a formula for the Qs, you can use that formula to show that these TKs, when they act on the Qs, you get exactly these normalized characters, which we know because by the Monahan-Nakayama, these are some integer ratios that we can calculate. So we want to therefore focus in order to identify all the Qs or the space spanned by the Qs for a given tau1, tau2. We just need to solve these eigenvalue equations. So we're going to solve that equation in the ribbon graph basis. So think about how these TKs act on the ribbon graph basis. So TKI acting on the ribbon graph will be some linear combination of ribbon graphs. And these, it turns out, are integers. It's the number of times multiplication of the elements of these permutations inside here. When you multiply the elements in a fixed orbit, you get elements in that orbit. So basically, these are integer matrices. So what we are having now is this integer matrices, and we have an eigenvalue problem. But we know the eigenvalue, so we don't even have to solve the eigenvalue problem because they are normalized characters. So the eigenvalue, therefore, so these are the matrices correspond to these TK operators. These are the eigenvalues which are known integers. So therefore, we just have to look for the null space of this matrix, which is all integers. So null space of integer matrices is a very nice thing. There are nice ways to build the null vectors. So if you have a matrix which is integer and you're looking for its null space, so you're looking for to span the complete set of vectors obeying this null vector equation, it suffices to look for vectors which are themselves integer vectors, and they can form a basis. So there's a nice fact about integer matrices. And in fact, there are ways to construct these integer matrix, these null vectors. And the way one does that is integer matrix algorithms. One way to do it is to take your matrix X and find what is called its Hermite normal form. So that means finding a matrix of a special triangular form called Hermite normal form H. And then U is a special integer unimodular matrix with determinant 1. So basically, there are algorithms for finding the Hermite normal form. And once you found the H and U, you know all the null vectors of X, all the null vectors of X. So that's a fact about I think I have some transparencies here. I won't really go through it for the sake of time. But basically, maybe I'll just go over an example. I don't think I'll do that because I want to get to the physics. So essentially, if you have if you're looking for the null space of an integer matrix, the null space is spanned by integer vectors, and there are nice algorithms in computational number theory or something to do that. Great. So the summary is we start with an integer matrix, this TK. Sorry, so we have these integer matrices MK. We have these normalized characters D. So we have a whole integer matrix. This is constructed from multiplying T's with E's, so a very combinatoric operation. There's a known combinatoric Monahan-Nakayama lemma. So there's an integer matrix, and there is this integer matrix algorithm, which essentially involves things like swapping rows, multiply by -1, add an integer multiple of a row to another row, all very discrete, finite things. So you can do that, perform these integer row operations on this very integer object, and you end up with a set of integer null vectors, and you count how many of these null vectors you have, and you get C squared. So in the space of integer linear combinations of ribbon graph vectors, in this space, there are sublattices of dimension C square, and there is a concrete algorithm to produce these null vectors, and you just count them and you get C square. So that's an application basically of tensor model mathematics to a kind of Kronecker coefficients. Turns out that this K of n is also a nice Hilbert space. There's a nice inner product on it. So it's inherited from the inner product on the group algebra. So sigma 1 tensor sigma 2. What's the pairing of one pair with another? There's a delta function. Essentially, you're saying that the permutation pairs form an orthonormal basis. So that's what this formula is saying. You get 1 if this permutation pair is the same as this permutation pair, and 0 otherwise. So using this pairing, you can form a sesquilinear non-degenerate pairing. First of all, we have a pairing on C of Sn tensor C of Sn. There's a subspace there, which is a subalgebra. So on that subalgebra, this leads to essentially these E's living in that subalgebra, these ribbon graph vectors, are linear combinations of things like this. So you inherit an inner product on that, which you can show is non-degenerate. Great, so K of n is an interesting space of linear combinations of ribbon graphs, and there is a non-degenerate inner product. So you can think of it as a Hilbert space. These operators TKI that I was talking about, which were useful in distinguishing the Fourier basis, you can show they are Hermitian operators, and you can build linear combinations of them, which are Hamiltonians. And you can, you can actually choose for generic choices of coefficients of these here. This Hamiltonian itself can distinguish the different Young diagram triples. So essentially, for appropriate choices, appropriate fairly generic choices of A's, you can do everything that I said before about finding the null space of an integer matrix. Essentially, you're finding the eigenvalues, the eigenspaces of this Hamiltonian, and the eigenspaces are expressed in terms of linear combinations of these normalized characters. These are the eigenvalues. Again, we know them because we know the normalized characters. They are known algorithms. So finding the eigenspaces, H V equals omega V is the same as finding H minus omega, the null space of this matrix. This is built out of these things and the associated integer matrices M. These are eigenvalues built out of these normalized characters. They're nice integers. Again, so now you have a square integer matrix, and you're finding its null vectors. In the previous case, that matrix was not square because there are three kinds of t's, and I had to stack all the t's together to build a linear operator. But here you can do it with square matrices by finding an appropriate Hamiltonian. Great. So these a bit of connection to physics. So we have this Hamiltonian, we have this quantum mechanics on K of n, and K of n has a basis of bipartite graphs. So there's a nice connection between bipartite graphs and branch covers. So, you know, we said bipartite graphs and one-to-one correspondence with pairs of permutations, with the understanding that this pair is equivalent to this pair, where I'm conjugating by the same permutation gamma in Sn. So tau 1 and tau 2 are in Sn. So these pairs are related to n-fold covers of the sphere. Given a tau 1 and a tau 2, you can define a third one, which is the inverse of the product. So tau 1, tau 2, tau 3 is 1. And these permutation triples describe for us, these permutation triples describe for us branch covers of the sphere with 3 branch points. The different permutations correspond to different monodromies around branch points. And you can work out the genus of the covering surface 2h minus 2 in terms of n, the Sn, where these permutations live. And there are some branching numbers which can be expressed in terms of the number of cycles of these permutations. So essentially, each of these bipartite graphs is a branch cover, okay, of the sphere. So you can think of this as a model for. So each of them is a cover. So, for example, this bipartite graph, we said it can be drawn on genus 1 surface. So there's associated with that, there is a genus 1 covering a sphere at 3 branch points. And the tau 1, tau 2 were 2 permutations that I gave you before. Tau 3 is the inverse of the product. Turns out it is also this permutation 1, 2, 3. So this is a branch cover. So it's a torus mapping a sphere. And there are 3 places on the sphere. So generic places is a branch cover of degree 3. So there are 3 sheets. At each of these branch points, 3 sheets meet. Permutations describe exactly how they meet. So for each of these guys, there's a branch cover. And we have Hamiltonians built out of these T operators. These T operators are permutations, basically. So if you have this tau 1, tau 2, 1, 2, 3, 1, 2, 3, you take one of these T's, you multiply it, you can get another tau 1, tau 2. So with the Hamiltonian, you can imagine an evolution where this torus mapping a sphere is evolving to some linear combination involving the torus and another cover. So this second cover I've got here is a genus 0. So you have essentially permutations encode a lot of information. They include these branch cover maps. So you have one covering. As this Hamiltonian acts on these permutation pairs describing this, it evolves into a linear combination of other permutation pairs which describe this covering. So we have a quantum mechanics where the states correspond to ribbon graphs, and the ribbon graphs themselves evolve, but the ribbon graphs themselves correspond to covering maps. So it's like a 2-dimensional surface, and these 2-dimensional surfaces are evolving. So in that sense, we have a combinatoric model describing kind of a membrane where you have, if you kind of think of this evolving, there's a time direction, and at a fixed time, you have this surface. So surface evolving in time, covering S2 cross R. So this quantum mechanical models have a very nice interpretation. These bipartite graphs and these covers, because they are covers with 3 branch points, these covers are known to be realized. Well, it is known that every curve which is defined over algebraic numbers admits such a 3-point branch covering to the sphere. And these maps are also algebraic, so they're described with equations involving polynomials in some indeterminates x, y, and z, with some coefficients which are algebraic numbers. So they are these coefficients are themselves solutions to polynomial equations with rational coefficients. So for that reason, these 3-point branch covering maps have nice number theory associated with them due to the Belly theorem. The connection to Belly theorem hasn't really played a big role in the connection with K of n that I've described so far, but maybe this is something to think about for the future. So a couple of remarks and open questions to wrap things up. So I said that these T2 up to Tn generate the center of Sn. But in fact, you'd only needed T2 up to Tk star, where in experiments with n up to 79, this k star was less than n, much less than n. So for 79, it was just 6. So you don't really need all these t's, you only need 6 of them. So one very interesting question is, how does k star of n, so the minimal number of t's that you need to generate the whole center, how does that grow as n becomes large? Another question is, so I've said that there's essentially an integer matrix. You have a null vector, there are the null vectors here, which live inside a lattice, and these null vectors span a sublattice, and the dimension of that, the number of these vectors is c squared, the square of the Kronecker coefficient. One question that people who are sort of computational complexity people, one thing they're interested in such a scenario, in such a situation, is, okay, suppose I give you one of these vectors, how efficiently how long does it take, how many steps does it take for you to verify that it really obeys the condition that you have specified? In our case here, as currently stated, this k of n, as we said, grows very rapidly. The dimension of that grows like n factorial. So at the moment, the algorithm we have given, it takes a lot of time, sort of super exponential in n, to verify that something really obeys this condition. So if you could find a way of modifying this or playing with this and finding a way to verify this null vector condition in time, which is polynomial, then this will get the computational complexity theorists very interested. So I gave a talk to a math community recently, and that's what I learned. But so far we have only used the linear structure in K of n, the Fourier bases, one ribbon graphs, one the Qs. We haven't really used any detailed structure. What is a minimal set of generators for this algebra? So one can hope that more detailed study of K of n might help make progress in that direction. We have these models that mathematically look like quantum membrane models. Can we build physical continuum descriptions whose quantization produces these models? There are discussions of non-relativistic membrane theories of Bethe-Horava. Can we make some contact with those using these combinatoric models? I mentioned this K of n comes in tensor models, where you're looking at degree n invariance. In tensor models, you're in general interested in all degrees. N goes from 0 to infinity. So you're interested in an infinite version of this as well. People in tensor models have investigated Hamiltonians, even more complicated than the ones I have described, well, more complicated than the ones I have described, which even mix different different ends. So tensor models could be an avenue towards continuum descriptions of these interesting quantum mechanical systems. So I'll stop here.
So let us thank the speaker for the very nice talk. So now we have some time for questions. If anyone has any questions or comments, please unmute yourself and please ask the speaker.
May I ask a question?
Yeah, please.
So this is more just a broad overview question. So what sort of number theory do you expect to pop up from this? And second part is that, have you thought of any particular questions that number theorists would be interested from what you just said today?
So I guess one of the things that people are interested in, so in this connection here, so let's say, well, in this belly map connection, so here, so I guess this connection was made in the late 70s by Belly, and then was discussed also by Grothendieck, and these bipartite graphs are also called dessin d'enfant. So one of the, so people have worked on that, and one of the links to, one of the things that interested Grothendieck in this subject was sort of the link between this concrete combinatoric aspects and these Galois extensions. So basically associated with these extensions, there is this group called the absolute Galois group, and one of the motivations was to, for the study of dessin d'enfant and their connection to branch covering maps, was, and I think continues to be, an interest in understanding how to learn about this group, which is a complicated group that not a lot is understood about, and how to understand the connection between that and this dessin. So these dessin have a lot of very concrete combinatoric data, and you want to sort of say which of the combinatoric data that you have here in the dessin are Galois invariants. So there's a lot of papers describing Galois invariants, which are constructed from these tau 1, tau 2 pairs. So for example, I believe the tau 1, tau 2 in general will generate a subgroup G inside the SN. So this is the monodromy group. So the group generated is a Galois invariant. And there are other things that people have studied. So the link between the kind of combinatorics I am describing, the Kronecker coefficients and Galois invariance properties of these dessin d'enfant or bipartite graphs. So the interface between Kronecker coefficients and that kind of Galois invariant side, that hasn't been studied, and it seems like an interesting question for the future.
Thank you.
Any other questions or comments?
And I have one question. So, so the combinatorics, the interesting structures you have been describing, so they appear in various different physics contexts, like tensor models and, for example, counting of geometry, like LLM geometries, or like or membrane theory, or Quiver gauge theory, etc. So I wonder if there is if you can sort of connect two quantities in completely different contexts, and therefore take advantage of the say common mathematical structures, and learn about so you use the inside of one physics theory to learn about the completely different theory or something like that. So
yeah,
has that actually kind of happened in one way or another, or in a sense your research itself has been motivated by that probably, but
yeah, no, I think well, for example, here in the story I was telling, I think there is a nice element which is like that, which is this, the study of K star of n. So it's a very nice, algebraic question about the group algebra of Sn.
yes.
It says Sn, the center of Sn, for every conjugacy class, if you take an average over the permutation, sum of the permutations in that conjugacy class, you get a central element, and that spans the complete set of central elements. And there's one conjugacy class, for example, for S3, there's one conjugacy class for every partition. So there are 3 partitions. Now, but and the number of partitions in general grows very rapidly, like e to the root n. Now, if you kind of ask, yes, that's right, all of them. So an arbitrary linear combination in the center looks like this, but can I find, just a small set like T2 and T3, and think about T2, T3, let's say A2, A3, A4 of T2 times T3 plus A5, T2 square, T3, and so on. So this kind of thing generating the center. What can I find a small subset? So this was actually motivated. The study of these small subsets was motivated by the studies of half BPS, giant gravitons, and essentially the reason for that, which I didn't get into here, was that these T2, T3, and so on, they correspond to, again, by Shuval, this is kind of SN stuff, and the common story here is Shuval duality, which relates SN stuff to unitary groups and so on. So quadratic Casimirs, cubic Casimirs, and so on. So if you have BPS operators made out of matrices, on these BPS operators, you can build differential operators, which look like UN operators, and you can build Casimirs out of these. So in fact, this question is related to what is a small set of Casimirs of UN that can be used to distinguish, all the operators of a fixed degree. And these people were interested in kind of integrability and information loss. They were saying that, okay, you have these LLM geometries, you have these multipole moments at infinity, properties of the gravity field at infinity, that you can measure, which determine on the gauge theory side, if you have n Casimirs, you can determine the Young diagram completely, and the Young diagram is a given LLM geometry. Now, but in practice, if you're measuring the multiple moments, you don't expect to be measuring all n. Maybe in reality, you can have multiple moments up to order n to the 1/4, which is related to the Planck scale in ADS 5 CFT4. So that's why they were interested in how much can you learn about the Young diagram or the LLM geometry using just a finite set of multiple moments. So that question translates purely in the symmetric group language to this question about what's a small number of T's that generate the center. And now this has implications for Kronecker coefficients, which is sort of something that other people are interested in who know nothing about half BPS. So I think this has one example, and I'm sure you correctly point out that this same mathematics appears in different places, and there may well be many more connections either within physics or between physics and other things.
I see. Thank you.
Any more questions? No? Okay, let us thank the speaker once again. So the next talk will begin in about, let's say, 20 minutes time, and it will be by Professor Tito de Mofti.
Thank you very much.
Thank you. Yeah, so let's see, I have one more question. So does this have any implication to the quiver gauge theory context? So as you know, you can, bi-partite graphs, and then it describes.
Oh yeah, that's right.
So
yes,
duo is the quiver, and well, in that case, each graph represents the theory. So
that's right. Yeah, so I guess I do wonder about this. So if you have a gauge theory in 4D, which kind of is, I guess, the data for the matter fields and so on is encoded in a graph.
Mm-hmm.
Now we start having interesting dynamics of the graphs. Mm-hmm. Is there some way to couple it to what's happening in 4D? Or are we talking about a 4D coupled to something else where different theories are talking to each other? I think this is a very interesting thing to think about. I haven't thought too far, but this is, a very good question.
I see. Yeah, so it's connecting different theories. So maybe you couple the quiver gauge theory to something else. There is algebra.
Yeah, it seems to me that you have to couple it. You have this data, and there's this nice dynamics. And I think this is a deep question, because coupling different backgrounds and what can you do by coupling different backgrounds? Is there some interesting physics there? I think this is the kind of thing we should be thinking about, because otherwise, string theory has plethora of different vacua, but if there exists interesting physical dynamics on these spaces, we have to think about how to couple them.
I see.
Yeah, I think it's very interesting.
Okay, great. Thank you. So yeah.
Okay, thank you. I'll take a little break and come back for the next talk.
Yeah, that's right. And then you also take a little bit of break.
Right, Masi, I just posted a chat paper on the chat. I think they talk about these Berry maps and relations to Fourier gauge theories.
Oh, yeah. Yeah.
Oh, you're aware of this? Okay.
I'm aware of that.
Okay.
I see.
But I don't know. So, for example, in that context, there is a Torre-Carabiao, and then there is a Fourier gauge theory, and then which can be translated to the Berry map. So, you can, there is a translation between Carabiao geometry and the Berry map.
That's right.
But, yeah. So, so that exists mathematically, but what physics we can extract from that, it's not completely clear yet. And
yeah, then we should talk about this. I mean, you already got me a Torre-Carabiao, so.
Yeah, and even there was technically interesting things about some of these papers in that the Berry maps. I read a lot in the Berry map literature, and most of the explicit construction is on the sphere. But in this construction, people are typically interested in the graphs on the torus. So it's much more difficult to write explicit maps, etc. So.
Yeah, well, yeah, no, in fact, some of this literature is by my buddy, Yang. In fact, I was in one of those earlier papers as well. Yeah, we didn't really, yeah, that has been the question. How much physics can you get of the theory from these diamond models? I guess you were getting they didn't code super potentials of n=1 theories. So I don't know what else has been done, but I think from the new stuff, what I find interesting is that now everything is dynamical. The graphs are dynamical. So what do we make of that? So yeah.
Okay. Yeah. Okay. Great. So it's great that there are new developments. So yeah.
Okay. I'll see you guys soon.
Okay, thank you.
Okay, so Tudor, hi.
Hi, Tudor.
So I'm going to try making you co-host so we can test your slides.
I want to connect with my iPad. And
okay, so I'll make all your...
And put the meeting coordinates manually.
Okay.
Just a sec.
Is your iPad connected already? Or? Oh.